Many thanks for inviting me to this prestigious European Microwave Association webinar series. I'm more on AP person, and then I don't come very often to a microwave, but I think we are doing something in common, and hence I'm very happy to come here and then talk what I'm doing here. And then I stopped my video because in the recording it may disturb looking at the slide set. So I stopped my video now, and then now I'm going to start the actual talk. So once again, thanks for coming to this meeting or this talk, and then for the next about 1 hour, I'm going to discuss about this radio wave propagation at the millimeter wave and the sub-THz frequencies, which is probably of interest for some of you who is looking for 6G. But this lecture or this talk is also meant for somebody who is not very well familiar with the electromagnetics, who is going to start learning those things. So that I borrowed the lecture slide from my doctoral level or even master level courses. So it's meant for also quite basics of wave propagation, which we probably it's probably useful at some point in the research life. Right, so I guess we go to the 6G, and then every corner of our life we see the wireless applications. So different environment, different applications. I mean, whenever we have those things, then the first thing which people wonder is, okay, then do we get enough signal power? What is the coverage? If we talk to the sub-THz, then how far we can make a communication? If it's the low frequency, how much interference are there? And usually when I'm discussing with the experts in microwave, then they tell me that, oh, I mean, you do research on wireless propagation, but usually you first have to do the measurement, otherwise you don't know anything. That's in one sense, one hand true. I mean, we always rely on measurements so that we can design coverage, we can analyze the interference, we can know where to place the base stations and so forth. But on the other hand, from our measurements, it's possible to get path loss model. It's possible to get how many RF chains or how many ADCs we can integrate into a sub-THz transceivers and so forth. So our measurement is finally converted to a, let's say, channel model, which you may hear every now and then to support the design of your microwave devices or transceivers. So in a nutshell, I'm doing measurements of radio propagation in different settings, different scenarios, different regions, different frequencies, which cover those application areas. And then when it comes to the cellular applications, then I think we can define different cellular scenarios depending on mainly its coverage area. The first one, the macro cells, that is the most traditional cellular systems, I would say, which have a base station on top of the roof, and then it is serving the users down on the street. And then they are usually like very wide cellular coverage, up to 1 kilometer. And if we go to the urban, suburban areas or rural areas, then it's even more, like up to 10 kilometers of the coverage we are expecting by putting a base station on top of the roof or on top of a hill, on top of a mast, and so forth. And then when we are discussing about the microcells, then it is meant for more dense urban areas like city center. And then usually the base station is integrated into the wall. And then it is having a smaller coverage compared to the macro cells. And then probably it is also serving some users to indoor. And then, but small cells or picocells, femtocells, whatever, We also install nowadays in the building so that we have dedicated coverage for the indoor users. And then as the last one, satellite links. That's quite a traditional one, but every now and then we still need it. And then we are going to see that it's going to be a part of the cellular wireless networks because in case we have very isolated rural areas, and in case we have some natural disaster like earthquake, the avalanche, or massive forest fire. If wireless systems does not work because of the outage of the power, then satellite link is probably one really viable last opportunity to be able to make communication for the life of people. So those are, the cellular scenarios that we have. And then in order to understand how much energy we receive from base station, then we need to understand not only of the power attenuation in the free space, but also because of the power attenuation, because of many mechanisms like reflection on the wall, penetration through the wall, deflection on the corner or the edge of the building, and then also scattering from trees, and then so forth. So those are something which I'm going to address in this lecture for the purpose of knowing their frequency dependency, meaning that, we now talk about the 6G, and then one of new points, new physical layer of the 6G is to use even higher frequencies than the millimeter wave. I'm not sure whether sub-THz radios are ready in commercial use for the cellular radios in the near future or far future, but that's the work that we are asked to do, whether it's possible to do, how much capacity, how much data rate, how much coverage we can do. And then I think this is the common interesting point between antennas and propagation and the microwave community, where the microwave experts know, what kind of semiconductor technologies are available, what kind of frequencies we can use, and then how much power amplifiers we can get out of the existing technologies, and what is the frequency dependency finally. So, the microwave experts knowing, the device side, semiconductor side, measurement side, then I'm the experts of the radio side. So I hope this talk is something which is complementary in terms of the interest between us. Device, I know more on the radio. Radio wave propagation, let's say. And then we cover the following the propagation mechanisms to discuss their frequency dependency. The first one is the free space, reflection, diffraction, transmission penetration, diffraction, and then scattering, and then also the mouthpass characteristics. And then finally, if time allows, I want to introduce some recent millimeter wave sub-THz measurements that we performed here, and also some interesting work coming already reported in the literature. In terms of material measurements, human tissue characterization, identification of the wave interacting objects at terahertz, and then how many mouthpass can we expect at the sub-terahertz. Those are something which is done here. And then if time permits, I would like to introduce some recent work, in this at the end of this lecture. Right. Then whenever I'm doing a tutorial or lecture, especially in Finland, when I'm doing a lecture here, if a teacher is just speaking and students are just listening, and then students are just thinking that it's just boring, and then I don't learn anything too much, and so forth. So I always put some time for audience or students to think. And then for that purpose, I give always some quiz so that teachers become silent, and then students are thinking more actively in some discussion environment or silent environment, and so forth. So whenever I was doing a tutorial of the wave propagation for 5G, I'm using this slide, to ask a question. So do you agree with the following statement? In line side links, the radios with the higher carrier frequencies like a millimeter wave are inferior to those with the lower carrier frequencies because free space attenuation is greater. So back then, I was always using this as a opening question, and then I started to feel that this slide or this question is a bit obsolete now, now because we are going to 6G. But nevertheless, I give you 30 seconds to think in yourself or discuss with your neighbors. However, I close my mouth for 30 seconds, so you just think for 30 seconds. Right, now it's 30 seconds have passed. I think you can think a lot of things within this silent time, and then that's a good, wrap up or self-reflection on what you know already. And if I can complement your knowledge, then we usually discuss about this Fries's formula, where we have a transmit antenna, which is the ideal point source, and then receive antenna, which have maybe some size of the antenna aperture size A2. And then in this case, how we calculate the power which is coming from the receiver side is first we calculate this power density, which is something which we can observe in this small area, given that the point source transmit antenna is located here. Then the point source is diffusing the power to all the directions, and then within this area we have this amount of power density. If we integrate this amount across all the unit sphere, then we get total power PT remaining. And then with this power density per square meter, this is actually watt per square meter is the unit. And then we multiply this with the antenna aperture size is A of the receiver. And then usually we want to express then the receiving power in terms of the gain of the antennas, and hence we can convert this antenna aperture size to the gain, and then we finally get this famous Fries's law. And then if we see this Fries's formula, then there's a lambda dependency, which tells that if we go to the millimeter wave, then we have a smaller power. And that is because we assume that here that we have like constant gain antenna on the receive side. So constant gain antenna like a dipole, it has a smaller size as we go from low frequency to the high frequency. For example, like quarter wavelength dipole, it's very tiny dipole which we can receive as a receiving antenna. But usually, we have a much bigger aperture size to receive signals, and hence, if we assume that like for antenna, we have a fixed aperture size, then we can get power which is proportional to the power density in watt per square meter. Then we don't lose anything in terms of frequency. So we say here that depending on the receiver antenna type, we may get a small amount of power, but if we are allowed to have the same aperture size, then we don't get any power penalty as we go for the higher frequency. So that's what we know already from the 5G. And then when this was a big debate at the beginning of the millimeter waves, whether we can really expect the energy to arrive or not. Then Samsung guys, they do measurements in a free space where we have a transmit antenna, which is isotropic, or like some dipole antenna. And then the receiving antenna, they change, they are like aperture size. And then according to the Fries's law, then we have 3 gigahertz, this curve. 30 gigahertz, we have bigger losses because it's assuming a constant gain antenna. But if we use patch antenna at 3 gigahertz, in the same size the patch antenna for 30 gigahertz, then this rectangular, and then the triangle, they coincide. That means that we don't lose any power. And then if we go to the antenna array on the transmit side, then we can even get a smaller path loss. So this was a very good measurement-based evidence that tells that the miss is really a miss. So, you know, we shouldn't worry about the millimeter waves that we cannot get any power. So that was the time in the 5G. And then now we become 6G era. And then I think that now I have to reformulate this question a bit. So that now the question becomes, without the line side connection, the sub-THz radios cannot be used for cellular radios communications applications because what we see as a multipass, reflection, scatter, deflected, they are too weak. Do you agree with this statement or not? I give you 30 seconds and then you again think about it. Right. So I think you have some thoughts on this issue. And then actually, I forgot to mention one thing. When talking about this, for example, the intelligent reflecting surface, the power that is we can deliver through the intelligent reflecting surface is also proportional to the power which is already available, or power density which is already available in the location of the intelligent reflecting surface. And hence, I mean, if it's quite a small sized intelligent reflecting surface, then what is coming from transmit antenna is already small, and hence having just small surface doesn't help too much. But of course, if it's a big sized surface, then I think it will help a lot. So, I mean, this Felice's formula tells a lot when it comes to also the effectiveness of intelligent reflecting surface, because, you know, we know how much power we can dig, you know, we can salvage from the free space, and then we can also deliver it to the receiving side. Right, so now in the 6G era, I think now it comes to the question whether we can rely on reflecting waves, deflected waves, scattered waves, and so forth, so that we can do the communication through them or not. And then that's one of the answers probably like we may have in the area of the antennas and propagation. I know that there are many more questions related to the sub-THz radio wave propagation, but I just chose this as a main question, which we are going to address in this lecture. So for that purpose, I'm going to introduce frequency dependency characteristics of different wave propagation mechanisms. The first one is the reflection. So here is the definition of reflection when plane wave is coming from region 1, and then it is incident to a flat infinite-sized interface. And then the other side, we have material with epsilon2, mu2, and then air, epsilon1, mu1. This is obviously 1 because it's air. And then now we can get reflection coefficient, and then transmission coefficient, which is dependent on these polarizations. So this is what we call perpendicular. My tablet works a bit weirdly, but nevertheless, this perpendicular polarization is meaning that the electric field is propagating in tangential format to the normal of this surface. So it's going this way, or it's going this way. And if this sign means it's a parallel polarization, means that the electric field is propagating on this line, either this way or this way. So depending on polarization, we have a different reflection coefficient, which is dependent on epsilon2, which is the permittivity value on the media, and then also the incident angle, and then also the transmitted angle. And then we have also knowledge of the material properties, which is, for example, like the most famous one is the from ITUR 2040, which is up to date from August 23. It gives for varying materials which we can find around us. We have a real part of the permittivity and also the conductivity value. And the conductivity is something which we can also convert to the imaginary part of the permittivity, which is given, which is a frequency dependent. So we see now that this coefficient B is representing the frequency dependency, and then if we have some water in it, then we have some dependency on the frequency for the real part. For the imaginary part, we see quite a bit of a frequency dependency. And then this is something which is already available, and it recently, the database has been continuously updated so that we now have a frequency up to 450 gigahertz. But as you see, if we want to study sub-THz, then we have a much less available database that we have to strive with. And then plotting material properties for the concrete and the plasterboard. For the real part on the left side, and the conductivity on the right side, we see that the real part doesn't change over the frequency, but the conductivity or the imaginary part of the permittivity, the lost part is increasing as the frequency increases. So this gives us some hint how the transmitted wave is affected by these properties. So I have another question here, which probably we may want to just address to exercise our brains. So I'm plotting two figures here. The first one is reflection coefficient, which is a constant across the frequency. The another plot, the reflection coefficient is for some reason fluctuating across the frequency. And those corresponds to either the infinite thickness material or 10 centimeter thickness material. So if we want to describe these figures, then which answer is giving us the correct explanation to them? That's something which I let's try this quiz by spending 30 seconds. I'm silent for the next 30 seconds. Right. My answer would be this choice A, which tells that if it's infinite thick, then we don't have any fluctuation. But if it's 10 centimeter thick, then we have fluctuation. And then this fluctuation is because we have waves which is coming reflected on the first surface. Second surface, we also have a reflection or even multiple reflections inside this surface, and hence they interfere each other, and then they are going to make this kind of fluctuation. But as you see, the frequency is higher, then we start to see less fluctuation. That means that the attenuation of this second way, like reflection from the second deeper side of the material, that's negligibly small, and hence we finally see only the reflection from the immediate surface of the interface. That means that we still have quite a stable power which is bounced on the surface. So this is just a recap of what I explained. And then going to the transmission penetration, then I'm plotting here the attenuation constant alpha 1 per meter. And then this is determined by epsilon, mu, and then also the frequency, also the conductivity. And then we see here that as the frequency increases, then attenuation due to the 10 centimeter slot in dB, it's a significant increase from like less than 1 dB to some tens of dBs if it's plasterboard. And if it's concrete, it's even harder. It's even severe attenuation. And then I compare, the formula from ITUR with this exact formula that we can calculate from the book. And then they agree to each other. That means that the ITUR document is a very reliable source of information to be able to calculate or estimate those things. And then, yeah, I think I spent almost 30 minutes, so I don't go with this quiz because there are still quite some slides. But what I wanted to tell in this slide is that here I'm showing the reflection coefficient with the wet and then dry ground. And then this top figure is from the wet ground. The bottom figure is from the dry ground. And then if we have the wet ground, then we have more reflections and a smaller transmission at 0.1 gigahertz of the radio frequency. And then on the dry ground, we have a smaller reflection and then more transmission. So that means that if we have a water, then that is producing more reflection and then less penetration. And then actually the water, if we are thinking about the human body blockage, if we are talking about the on-body communications and so forth, then human body is almost all water. And hence it's necessary to know about the permittivities of the water, which is actually given by the debye dispersion model in this formula. It's described by the initial or DC permittivity value, which is 80 in terms of the real value, real part. And then when it is optical permittivity, which is corresponding to this permittivity at a few hundred gigahertz, then it becomes 6. So there are some smooth transition from 80 to 6. And then the radio frequencies which we operate in radio applications, they are usually between those DC to the few hundred gigahertz so far. And hence this device model is a very good model to be able to know how it may look like for the frequency of our interest. And then imaginary part that is changing its value. Interestingly, it peaks at like 15 gigahertz and so forth, but again, it decreases its value after that, and then finally it reaches some values close to 15 or so at 60 gigahertz also. And then because we are almost water, we can use or actually when we want to know human body tissue permittivity, then we know that the human tissue permittivity is described by this Cole model, dispersion model, which is based on this device dispersion model, which has the similar formula as the device model, where we have the relative permittivity at the DC. We also have the relative permittivity at the optics frequency, and then this difference values here, and the initial DC. Oh, sorry, the optics value is here. Then we have some valuation from DC to the optics frequency, and this parameter is alpha, is this broadening parameter, which is probably dependent on the tissue, like blood, bone, brain. I mean, they are well parameterized by experiment by this Gabriel. I think this is something which people usually refer to. I think you may already know this, but I just want to remind, because this is always with the 100 gigs, and now if we are going to talk about the sub-THz, then so this is this model is something which we need to check. It's already available up to 100 gigs, but sub-THz, I think we have to start once again, making a base so that we can analyze materials or interaction between human and then waves, so that we can analyze sub-THz cellular values. Right, now another big question. So I want to reflect within yourself if the link of selection loss frequency dependent. If so, in which way? So I'm again silent for 30 seconds, so you can think by yourself what you think about. Right, 30 seconds have passed. And then the answer which I would provide is yes, it is frequency dependent. And then right, so in order to understand that one, I'm going to introduce first about the Fresnel zones, which is a very essential concept to understand the wave propagation in the radio frequency. So the Fresnel zones are defined by the ellipsoids. And the first Fresnel zone, for example, is this ellipsoid where the transmit antenna and the receive antenna are the focal points of this ellipsoid. And then definition is that we have line sight distance R0, and we have some reflected wave which is have a propagation distance of R1 plus R2. Then in this case, the propagation distance difference of propagation distance between this line sight and this reflected wave is half the lambda. So that's the definition of the first Fresnel zone. In the second Fresnel zone, then that's the case for that is defined by the line sight and then the reflected wave on this ellipse to have a propagation distance difference of lambda. And then we can also define this width or height of this Fresnel zone HF, which is dependent on the distance between transmitter and receiver, which is R1 plus R2, and also the wavelength lambda. So that means that the higher the frequency, then this width of the Fresnel zone becomes smaller. So that's something which is very important to remember now. And then next, I'm going to explain about this Huygens' principle and the secondary sources. So if we want to analyze this point source radiating spherical waves to the outside world, then we can analyze this the equiphase plane, which is this plane, just by this original source, or in other ways too. The other ways means that we can replace this original source by the secondary sources, which is located on this line, which is the spherical wavefront created by this original source. This is the original source. And this is the secondary sources. Secondary. So that means that the original source is creating a spherical wavefront, And that spherical wavefront is creating new sources, which we call secondary sources. And each of the secondary sources are making a spherical wavefront as a new source, and finally creating the same source as the original source, which is this spherical wave. So that means that if the wave is propagating, then this wave propagating wavefront is considered as a secondary source, which replaces the original source. So this is a Hoyle's principle on the secondary sources, which probably you learn in a university or in high school or wherever. And then if this is your first time, then I think it's good because this is very essential to understand, for example, diffraction. But before that, I'd like to understand the plane wave propagation using these secondary sources. Now we have this incident wave. And then incident wave is, for example, creating secondary sources on this plane, which is YZ plane at x equals 0. So the original incident wave is replaced by this rectangular plane where we have secondary sources distributed everywhere. And then each secondary source is propagate or creating the spherical wave to this observation Alex. And then what we can observe in this observation point Alex is the sum of waves, spherical waves created by secondary sources, which is distributed on this YZ plane. So on the Y domain from minus infinity to plus infinity, for Z domain from minus infinity to plus infinity, we integrate the contribution of spherical waves coming from each source. Then this is the source, which is corresponding to the original plane wave. And then we observe something at the receiver. So that's something which we want to, this is the understanding of the plane wave according to the Hoyle's principle. But now, because we are originally receiving instant plane wave, so we should see the signal only from this direction. I mean, we have some plane wave, how to say, original direction that we get signals from. And then we should not see any signals coming from any other directions. So we may wonder whether original plane wave and then radiated spherical waves from secondary sources, they are consistent to each other or not. It is consistent because of the slides which I'm showing here. So each of those places are radiating a spherical wave and then making some contribution to the receiving field, the receiving side, receiving point. Now, on this right side of the figure, I'm plotting the magnitude and the phase of the field, which is observed due to the secondary sources on this y equals 0, x equals 0, and z changing from -5 meters to 5 meters. And then if we look at this blue curve, which is magnitude, then if we have, to say, z axis going away from the origin, then we have a lower power. But looking at the phase, then if we have z at 0, then spherical wave gives us some phase. But then as the spherical wave, the secondary wave location is going away from this origin, then phase observation from this secondary source is starting to fluctuate very quickly, as you see on this side. And then finally, what we observe as a receiver field is the integration, some of those fields from various secondary sources. And then if we see that phase is fluctuating randomly between 0 and 180 degrees, then we see that they are almost canceled to each other with the opposite phase and then almost the same magnitude. And hence, finally, what is making a contribution as the instant field is only this region of the secondary sources, which provides this side, this area of the secondary sources, or this area of the phase and the magnitude. So that means that secondary sources contribution outside this area is something which we cannot finally see. And only some region of the secondary sources, we see its contribution. And that region where we see the contribution of the secondary sources is called, it's proportional to the first precedence zone. And that tells that different from laser, in the radio wave propagation, in order for the radio waves to propagate, we need some space around the line side. It's not just a line which is connecting, which is delivering the energy, but the line around some volume that is providing us some space to deliver the energy from one side to the another. This is a very important concept to understand the frequency dependency, because this can also allows, this allows us to understand the diffraction coefficient here. So, we have now incident plane wave, and then we probably have some secondary sources on this plane, YZ plane, at x equals 0. Now, half of them is absorbed by this absorbing screen. And in this case, then what is observed at this observation point with the varying y height, y smaller than 0 means it's in the shadowed region, it's low, and the y greater than 0, that means the lit region where we can see the incident wave. And then the eventual the equation or solution of the diffracted field is the sum of original plane wave and then also the diffracted field. And then when we see, when the observation point is negative, like below 0, then we don't see this guy. But we see the wave which is corresponding to this z equals 0, where spherical wave is not cancelled by any other sources. For example, if the wave, there's spherical wave or radiated field from secondary sources here, but this field does not contribute to this observation point because there's another source which is next to it, having a 180-degree phase shift. They cancel to each other. But at this edge, we do not have any other source to cancel the signal, and hence we have we can see that this source is contributing to the signal. So this diffraction coefficient is described by is proportional to square root of lambda, and hence it has its value is smaller as the frequency is increasing, and hence sub-THz. Most likely, we cannot expect too much of a contribution of diffracted path in wave propagation. So now we have 15 minutes to late. Sorry, 15 minutes to half only. So let's cover the rest. Then when we see that diffraction of the wave, depending on the how much energies, how much first precedence zone is shadowed, then we see that if we have a transmitter receiver link, which is just above this absorbing screen, then we have 6 dB losses. This corresponds to this H equals 0. And then H equals 0 means we here have 6 dB losses. 6 dB means 1/4 of the power, only 1/4 of the power is delivered from transmit side to the receive side. And actually, this is not the 1/2. It's not half of the power coming, but only 1/4 of the power coming, because what is absorbed is electric field. It's not the power. We have to always make sure we have to always know that what is propagating is the field, not the energy. So half of the field lost means 1/4 of the energy arriving at the other side, and hence it's not 3 dB but 60. And then talking about the frequency dependency, then the Fresnel zone, which is responsible for delivering the energy at the radio frequency, its size is described or proportional to the square root of lambda. So it's becoming smaller and smaller if we go to the higher frequency. So if some of this, it takes smaller, like tip of the absorber is distracting the TX-RX link, then at the 60 gigahertz, easily this energy propagating area is blocked. But here for the 2 gigahertz, then Fresnel zone is bigger, then it's less easy for blocking the energy to deliver from TX side to the RX side. So diffraction loss, human body shadowing, that is something which is becoming much more severe if we go to the higher frequency. And then finally, I'd like to discuss about the scattering. And then here I put another discussion item, but I don't go with that because we soon run out of time. So in case we have omnidirectional antenna on transmit side, on the receive side, then this omnidirectional antenna is illuminating all flat surface, and hence we have secondary sources everywhere. And then they are all making radiation of a spherical wave to the receiving side. So the receiving antenna can see a secondary source contribution of the spherical wave from all the regions of the flat surface. But finally, according to the Snell's law, we know that it's only this point which is making a reflection. So why we don't see contribution of these guys, which is also radiating a spherical wave? And then the answer is that it is similar to the previous case where we see, spherical secondary sources distributed across the plane, but only part of them is finally seen because otherwise they are canceled in terms of the phase. So that is also explaining, the reflected field. And then that's something which we can also utilize to analyze the scattering. So here we have a rough surface. And then we have, there's a height difference. There's also, the change in the speed of this roughness of the surface. So now, how many points we see that wave is reflecting from? It's now not only this original reflection point for the flat surface, but we may also have some other points where the phase is not necessarily canceling in terms of the secondary sources. And hence, we see waves not only coming from specular or this reflection, which is the reflection angle, which is the same as the incident angle, but also from reflection from other angles too. So this is an example of, we fix the RF to 200 megahertz, which is the 1.5 meters of the wavelength. And then I changed the surface roughness from 1 centimeter to 32 centimeters. Then if we have a smaller roughness, then we see that the wave, this is 45 degrees. Then we also see that 45 degrees is the main energy coming reflected back. But so the roughness goes higher, then we see that the energy is going to the other directions too. On the right side of the figure, we see that the varying RF with the 1 centimeter roughness of the standard deviation. And then as the frequency is higher from 0.2 gigahertz to 5 gigahertz, then we start to see less power going to the specular direction. Specular means the incident angle, the same as the reflecting angle. And then more energy going to the other directions. So now thinking about the sub-THz, I think angular selectivity on the rough surface becomes very, very high, means that energy, it's not because surface naturally have its roughness, and then If it's concrete, if it's some plasterboard, it has its own roughness on the surface. And probably for some surfaces, it's not considered as flat anymore as we do for the lower frequencies. And then it may be so that those roughness may affect the scattering or lost energy to the scattering, and hence sometimes that can arrive on the receiving side, but that's not always the case. So I would say that according to what we observed in the measurement, then mouthpass becomes in general sparser compared to the low frequency, which we have as a measurement evidence, but that's something which we can expect according to this theory of scattering from dependent on the frequency. So as a summary, I just summarize which propagation mechanism is dependent on the frequency. So reflection, that's least dependent on the frequency, while scattering, diffraction, shadowing, transmission, penetration, that's more heavily dependent on the frequency, and hence we may not be expecting to rely on those propagation mechanisms if we are going to establish a radio link between transmit and the receiver. And then as we see the free space path loss, whether the energy depends on the frequency or not, that depends on the antennas. So if we are allowed to have a big antenna, then of course, depending on beam forming or beam steering technique, we can ensure even the higher power received compared to the legacy band. So that's something which is the case already for the 5G, and it's even more important for the 6G. And then that's the main thing that today I want to deliver to you. And then rest, I have some slide set, but I think I'm run out of time. And then I'd like to show a bit of recent finding from our sub-THz measurements, how what we guessed so far is applicable in practice in the sub-THz measurement. So the first of all, we did channel sounding at 140 gigahertz in outdoor environment, and then indoor environment, outdoor environment, and then we were like rotating horn antenna across Azimuth angle, and then another side of the antenna is a Baiko antenna, and then we were checking whether it's possible to see any reflected waves in the environment. And then this is the result. So this axis is the delay, and then the x-axis is the angle of the horn antenna, and then lit region is the signal observed. So we see here that there are quite many actually mouthpass components coming from different parts of the environment. And then we try to check which object is actually causing those mouthpass. And then we found that if we are trying to fuse the data of this measurement with this map of the environment, then we noticed that even like a fourth order deflection exists in the environment. So that was quite surprising to me, because I was expecting that there's no mouthpass at all. But even fourth order reflection exists, and that's actually something which is supported by what we saw in today's lecture earlier part, because the reflection is something which we can count even for the sub-THz. And then this is the power shared by first order reflection, second order reflection, third order reflection, and so forth. And then if it is the long line side channels, which is this the red and then the blue bars, then we see that even fourth order reflection is contributing 20% of the total power. That was really, really surprising result from this measurement. So I would say that even sub-THz, I think it may be possible to rely on spatial eigenmode transmission if you want. But what we also noticed is that the number of channels, or number of independent channels, or number of mouthpass components may indeed be smaller compared to the lower frequency, because when we were analyzing the MIMO channel rank for a MIMO channel realized by a phased antenna array, then we see that it's never full rank, but the rank is somehow restricted to 6 in the indoor, and then 4 in the outdoor site, which we measured. I mean, that's very specific results, and hence I'm not sure. There may be some site where the full rank channel is given, but nevertheless, this is something which I was also expecting, that because of the more angular selective scattering effect in the sub-THz or the higher frequency wave propagation, then we see less amount of multipass to be observed compared to the lower frequency band. But still, it's possible to do spatial multiplexing if we want. That was quite surprising results from my recent analysis. So that's something which I'd like to conclude this talk. I skipped quite some slides, but I think I was able to convey the main message that whether we can expect the same transceiver structure, same number of antenna, same extent of path loss, or we can expect the same number of multipass or not, or we can expect the same shadowing effect compared to the legacy 6 GHz. That's something which we can know by knowing frequency dependency of propagation mechanisms, and then that's the foundation to to define, for example, 3GPP channel model, or to understand the how to say link budget, and then and also some the device specifications that you may have. And then for that purpose, it's very important that we have measured evidences, but measurements are expensive, and then it takes time, cost. It's a human, so not many people can do the measurements. So if there are measurements that is reported by anybody, I really appreciate. And then I really I'm looking forward to further measurements which is done across the world. So that's it. So thank you for listening to my lecture. And then I'm open for questions and then comments. Thank you.
Yeah, thank you, Professor Haneda, for the very interesting talk and the very impressive experiments shown in the end. I'm sure there are questions from the audience. You may either enter them just into the chat if you make sure that they reach us, or using the Q&A panel. And yeah, I would read them once more if you send something to us, and I'm sure Professor Haneda will answer them.
Yeah, I saw quite comments answering to or responding to my quizzes. I'm very happy with that. Thank you very much.
There's a question on time varying effects due to, for example, wind blowing on leaves, and how to address this in a channel measurement, or even in a channel model afterwards.
Yeah, that's a very important and very good question. So yes, time. Channel is never repeating. It's never reproducing. So the channel condition that I now enjoy is something which we never observe in the future. I mean, because leaves flowing, and then the wind is blowing, and then rain is there, and so forth. So yeah, but still, it's possible to make a sort of reference model. Reference means that the window, not window, but the leaves, and then it's the input impact on the radio link is affecting in a statistical manner. With 90% of the time, we see this much of the losses, and then 10% in the best case, we have this small amount of the losses. So that kind of thing is something which we can derive by the measurements, and also based on extensive simulations. But as you know, as the frequency goes higher, then simulations and measurement that becomes very challenging. So again, I'm mentioning that now those measurement-based evidence is really lacking to be able to analyze those things. Thank you.
Yeah, maybe in the meantime, I have a question as well. So you showed in a very nice fashion that yeah, the assumption that free space path loss is increasing with frequency is not true under any circumstances. So if you use aperture antennas or antenna arrays, you can yeah, compensate or even increase the transmitted power due to beam steering. However, if you increase your, or if you fix the physical size of the antenna and you increase the frequency, you increase the gain, of course, but also the far field distance increases. So you're getting more into a near field scenario if you keep the aperture size but increase the considered frequency. Have you any comment on how this will impact on above 100 gigahertz communication?
Sure. That's a very good question, because above 100 gigs, if we want to utilize that radio band for, let's say, cellular applications where the communication over the N-loss non-line site scenario is really important or must, then I think usually this far field near field issue is not a problem, if not a big problem for like point-to-point link, where link distance is usually a few kilometers or like even 10 kilometers and so forth. But if we want to analyze the link with just 30 meters or 100 meters with the pencil beam antenna, then indeed, the far field assumption may not be fulfilled anymore because the distance is so short. So that's another actually a challenge of wave propagation, where we cannot think of antennas and wave propagation anymore in a decoupled manner, but we have to do the simulation with the antenna really a part of the environment. So sub-THz even yeah, makes a lot of challenges to us, and then that's a very pressing challenge that now we are addressing. So you predict the problem that we already have very well. Thanks for the point.
Okay, thank you. In the meantime, there was another question on environmental pollutants and how they affect the transmission, or if you have any clue which pollutants are more crucial in millimeter wave range, maybe compared to UHF.
I'm not expert on, for example, like there are some absorption of terahertz energy or terahertz waves depending on some molecules like H2O, O2. That's something which is known, but honestly speaking, I don't know about how, let's say, the other pollutant materials are affecting or it appears as absorption spectrum at the terahertz band. So that's a very good question, and I will have to study about it to be able to answer in a firm manner. Sorry, I cannot answer to that now.
I guess that's okay. Yeah, are there any further questions from the audience? There's another thing. The question is, Fresnel clearance is greater at higher frequency, so one could think that loss due to cluttering with air gaps, small canopies, for example, may not be a problem.
Yeah, I think that's an interesting point. I mean, I think this question is, or this comment is telling that, because Fresnel becomes smaller as the frequency increases, then even a smaller hole is something which like a sub-THz can penetrate or can go through without any extra loss. While if it's a low frequency, then present zone is bigger, and then smaller hole doesn't help to let the waves propagate. That's a very interesting observation. And then my comment on that is that usually, hitting a very small, narrow hole is not a very easy thing in a cellular communications, where we expect that like mobile device is moving. And furthermore, penetration loss at the 2 gigahertz is anyway not that much. I mean, as we saw in penetration loss curve dependent on the frequency, then at 2 GHz, just having a smaller disturbance on the frequency zone doesn't make too much of penalty to the link. So therefore, finally, I think 2 GHz is still robust in terms of the clearance of the blockage. But this is a very interesting viewpoint as to the clearance of the Fresnel zone, because I have never thought in this manner. Thanks, thanks for this comment.
Okay. So maybe if there are no further questions or comments right now, yeah. Oh, no, maybe there is. Okay. Yeah, thank you, Professor Haneda, for this very interesting talk once more. It was a pleasure to have you here in this format. And yeah, looking forward to further discussions in the future, maybe.
Good. Thank you.
Yeah, everybody else in the audience, thank you for joining us to this talk, and yeah, stay tuned for upcoming events. Bye-bye.
Bye.